Hey everyone, so today we're going to be looking at how to write formulas. We did a little bit of this when we were looking at the special types of nomenclature. This one is going to be looking at just generically molecules, ionic compounds, and acids. So let's go ahead and get started. We're going to first start with writing molecules. So just a quick reminder that molecules are going to be covalent compounds. Generally speaking, molecules are composed of two or more nonmetals covalently bonded with each other. Now, what's really nice about these is that when you're looking at molecules, molecules are going to be compounds whose names are always written with prefixes, and the prefixes that I'm referring to are the mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. These are indicating the amount of the element that is within the compound. Hopefully, these are fairly familiar phrases or words that you are already comfortable with. But if not, this is a good time to kind of start memorizing them. What's really nice about this is that if you see a prefix, you pretty much already know that you just need to indicate the amount of that element within the formula. So, for example, carbon tetrafluoride. Carbon does not have a prefix, so there's just going to be one of it. Tetra, the prefix tetra is 4, so it's tetrafluoride, so it's going to be CF4. Carbon tetrafluoride has one carbon for every 4 fluorines. The next example here, we have dinitrogen tetroxide. Di, remember, is the prefix 2. Tetra is still the prefix 4, so we have 2 nitrogens and 4 oxygens, so it's going to be N2O4. And then the last one, phosphorus. Phosphorus does not have a prefix. The prefix tri, though, is 3, so this looks like it's going to be Cl3, so phosphorus trichloride. Once again, notice that all of these are 2 or more nonmetals bonded to each other. Carbon and fluorine is a nonmetal. Nitrogen and oxygen is a nonmetal. Phosphorus and chlorine is a nonmetal. So once again, molecules will always have the prefixes, 2 or more nonmetals. Pretty straightforward. We like naming these, I think. So moving on, we're going to be looking at ionic formulas next. Remember, an ionic compound is going to be a chemical that is composed of a metal and a nonmetal, specifically a positively and a negatively charged ion. Opposite charges attract, so bringing these things together is based on the Coulomb's law. Opposites attract the attractive force between oppositely charged ions. Now, as far as these go, even though ionic compounds are composed of charged particles, the ionic compounds themselves are neutral. What this means is that the positively and negatively charged ions must come together in certain ratios such that the overall charge difference between the positive and negative is 0. And sometimes that means we need to add more of one type or more of the other in order to get that +2 and -2, +6 and -6, depending on what that opposite number must be. So for example, let's go ahead and check out calcium and chlorine. Now, generally speaking, calcium is in the second row on the periodic table. That means it likes to form ions with a 2+ charge. Chlorine is a halogen. It's in the 7th row on the periodic table, 7th column on the periodic table. So it likes to have a 1- charge. That means when these combine, I need to have the appropriate amount of each of them such that the overall charge is 0. So if I were to just bring 1 calcium and 1 chlorine together, that wouldn't work. The calcium and chlorine don't have equal but opposite charges. So one of the ways we go ahead and do this is by bringing more of the chlorines into the ionic compound of calcium chloride. For every 1 calcium, which has a 2+ charge, you need 2 chlorine ions. And that means the formula is going to look like this, where for every, once again, 1 calcium, which still has a 2+ charge, so this calcium here still has a 2+ charge, there are 2 chlorines with a 1-, but we know that 2 things with a 1- is 2 minus. So 2 plus 2 minus equals 0. This compound that I've written down here is neutral. It is neutral. So let's go ahead and try it with a little bit more challenging ionic compound. We're going to go ahead and look at aluminum and thiocyanate. Aluminum is in the third column on the periodic table. Aluminum is going to have a +3 charge. It generally will lose 3 electrons, 3 plus. Thiocyanate is the polyatomic ion, SCN 1 minus. So it's got 1 sulfur, carbon, and nitrogen covalently bonded with a 1 minus charge. So as far as this formula goes, it seems to me that we need to go ahead and have 3 thiocyanate ions for every 1 aluminum. And the formula for this will be AlSCN3. Now notice one thing here. There are parentheses placed around polyatomic ions. When there's more than one. When more than one. And basically it's just saying, hey, there are 3 little subunits here, 3 SCNs that have a -1 charge. So it's kind of like an SCN up here, 1 minus, SCN over here, 1 minus, and SCN over here, 1 minus. Notice 1 minus. Notice here that the sum of the negative charges is going to cancel out with the +3 charge down below. All right, awesome. Last example here we're going to go ahead and look at is going to be magnesium and sulfate. So magnesium is in the second column on the periodic table. So because of that, it's going to have a 2 plus charge. Sulfate is the polyatomic ion, SO4 2 minus. And what's really nice about this one is that they have the same charge, but opposite sign. That means that all you need is one of each of them in the formula. So magnesium is 2 plus, sulfate is 2 minus. It's just going to be MgSO4. So if you have just one polyatomic ion, notice that you do not need parentheses around it. Though writing parentheses around something when there's just one of them isn't the worst thing. It's just not really ever like that in the real world of chemistry. Beautiful. All right, so going ahead and moving on, we're going to finally look at acids. Now, a couple cool things about acids. Remember, acids are molecules. They are going to be 2 or more nonmetals. It's always going to be a hydrogen with some other set of non-metals. So there is a covalent bond there, but what's kind of funky, what's kind of cool about acids is that they behave similarly to ions when they're placed into water. And we'll discuss this more in detail later. But the reason that they have their own class of naming is because of how they behave when they dissolve into water. So as far as this goes, their formulas can be determined based on charge, even though the elements are not charged within them. So with that being said, we're first going to look at binary acids. Now, notice the prefix bi. The prefix bi means that there's only 2. So these are going to be molecules that have hydrogen and another element or polyatomic ion without oxygen. Now, generally speaking, we see bi, we think 2, but really this is your indicator that it's a binary acid. There is no oxygen present. So as far as this goes, when you see the word acid, I want you to think of H1 plus. As we will begin to see here, hydro, the prefix hydro, does not mean the hydrogen ion. So for example, let's go ahead and look at hydrobromic acid. The second you see hydro, you're like, okay, cool. This is a binary acid. That means the chemical I am looking at is going to be this chemical here, which is bromine. And we know bromine has a 1 minus charge. And then the acid tells us that it's the hydrogen ion, 1 plus. So hydrobromic acid is quite literally just a hydrogen ion and a bromine ion forming a covalent bond, so HBr. This right here is going to be the formula for hydrobromic bromic acid. Moving on here, we have oxyacids. And if binary acids are going to be acids that do not contain oxygen, that must mean that oxyacids do. Generally speaking, these are going to be hydrogen bonded to a polyatomic ion with oxygen. And as we saw earlier with the polyatomic ions, they will generally end in ate or ite. So like sulfate is SO4 2-, and sulfite is SO3 2-. And remember, the difference between ate and ite is the number of oxygens within the polyatomic ion. Now, the reason that I bring that up is because those endings are going to change based on if it's ate or ite. Remember, acid is the indicator that there is a hydrogen ion. So with these, with oxyacids, they never use the prefix hydro. Hydro, remember, is reserved for binary acids. So as far as this goes, when we're looking at nitric acid, and notice it's not hydronitric acid, we know that this prefix here, nitric, nitrogen, is something related to nitrogen. So just as a reminder, when you see IC, that comes from the suffix ate. So ic and ate are related to each other. So if you have nitric, that must mean that we're looking at the polyatomic ion nitrate. So this right here is going to tell us that it's NO3, 1-, that is nitrate polyatomic ion. And then the acid, remember the acid is the thing that is giving us the H+. Based on the charge, 1+, 1-, we're going to get HNO3. Try that one more time, HNO3. And there is our formula for the oxyacid nitric acid. Notice it's not hydronitric acid because, once again, hydro doesn't mean hydrogen. I know, it's the worst. Acid is the thing that indicates there is a hydrogen there. So I think I have, let's see here, yeah, 2 more examples of oxyacids. We have sulfuric. So sulfuric, remember, ic comes from the polyatomic ion ending ate. So ic and ate, so that means it's sulfate. This is going to be SO4 2-, and acid tells us it's the hydrogen ion. For every 1 hydrogen ion, for every 1 sulfate, it seems that I'm going to need 2 hydrogen ions. So this is going to be H2SO4. Sulfuric acid is probably one of those chemicals that you should have on the back of your mind anyway, memorize. It comes up a whole heck of a lot in this class. And then when you see the OUS ending, us is going to equate to the polyatomic ion ending ite. So this is going to be phosphite, and phosphite is PO3, 3-. The acid is H1+. So therefore, this is going to be H3PO3. Wonderful. Don't forget, there is a graphic organizer that follows along with this. So if you have any questions, feel free to shoot me an email. Thanks, y'all.